Alright, so for this video I'm going to be reviewing glycolysis and how we get from glucose to our pyruvate. Anaerobically, we move to lactate there at the end, but I'll get to that. I also have a puppy, so if you hear some scratching or pawing, it's because he's beneath me, fighting for attention down there. Alright, so first things first, we have glucose circulating in the blood. Hexokinase then acts upon this and transfers a phosphate group from ATP to G6P. So glucose 6-phosphate. The 6, the numbers show where the phosphates are. That's the nomenclature that I've used throughout. This is also where glycogen is. Once we activate glucose from the plasma, it gets stored essentially as this G6P. So worth noting is this is stage 1, the energy investment stage. We have 2 ATP that's used coming from plasma glucose, and we have 1 ATP that gets used if we start with glycogen. So from G6P, we have an isomerase, which rearranges the carbons and makes it a fructose 6-phosphate. And then from here is our rate-limiting step with phosphofructokinase. High levels of AMP, ADP, or increased pH are going to stimulate this process, meaning we're low in energy, we need to make more energy. And the reverse is true for inhibition. ATP, creatine phosphate, and citrate levels will inhibit this step from going any further. ATP is used here again to transfer their phosphate group to the fructose 1,6-bisphosphate. And from here, what I've done, so as we move into stage 2, which is the energy harvesting stage, I've only shown one process as opposed to the dual process which normally occurs. So instead of showing both pathways, I've just shown one, and it's known that you repeat this twice. Okay, so we go from fructose 1,6 to G3P, which is glyceraldehyde 3-phosphate, using an aldolase enzyme. From here is where we get our first oxidative energy coming from the NADH, the G3P dehydrogenase adds electrons to the NADH and ions, so that we can use that later on down the shuttle for the electron transport chain. So we go from G3P, we dehydrogenate it, we take NADH out, and we have 1,3-bis phosphoglycerate, I believe. And from here we use a kinase, and we form an ATP molecule from one of these phosphates attached to that 3-carbon member right there. And then it gives us 3-phosphoglycerate, so the 3 is the phosphate, where the phosphate is. We then use a mutase, which changes it into 2-phosphoglycerate, and then we use an enolase to make it phosphoenopyruvate, which is one of our higher energy molecules, which we then transfer into pyruvate using pyruvate kinase, and we get another ATP molecule out of this. So this is one side. Now we repeat this twice, and we have 2 NADH, and we have 4 total ATP produced. However, we also had 2 burned in the first, assuming we start with glucose. So our net growth of 2 ATP and 2 NADH to be used later. Aerobically, we go to acetyl-CoA, which starts the Krebs cycle, which I'll get to in the next video. Or anaerobically, we use a lactate dehydrogenase to make lactate. And I believe NADH is recalled from this as well, another area similar to how we get NADH from pyruvate dehydrogenase. But I wasn't entirely sure, so I didn't include that. But dehydrogenase, explains that we're pretty much getting electrons and ions out of it, so there should be an NADH there. And then it transfers into lactate, which is gluconeogenic. It goes back to the liver, and we pretty much start this whole process over. This is in case we are under anaerobic conditions.